I'm working with a dataset that has 100 different characteristics, features, and information on 500 different things, samples. Think of it like 100 different questions asked about 500 people. To ensure my model isn't just memorizing the data, I'll use 5-fold cross-validation. That means I'll split the data into 5 equal groups. I'll train the model on 4 groups and test on the remaining 1, repeating this process 5 times so that each group gets a chance to be the test set. This helps me get a more accurate idea of how well the model generalizes. I'm building a model to predict a continuous value. It's like predicting house prices based on size, location, etc. After training, my model will tell me which features are most important for making predictions. The model will provide me with weights, coefficients, associated only with the important features, the others are effectively zero. Think of it as a recipe where only a subset of ingredients contributes significantly to the final dish. The model will pick the best features step by step. At each step, it finds the feature that best helps explain the remaining part of the data that's not yet explained, a bit like solving a puzzle one piece at a time. To evaluate my model, I'll measure how far the model's predictions are from the actual values using the mean squared error, MSE. Lower MSE means better predictions. I'm using a specific technique called orthogonal matching pursuit, OMP, to select features and improve the model's performance through cross-validation. OMP is an iterative feature selection method which selects features based on their correlation with the residual error at each step, and cross-validation helps estimate how well the model generalizes to unseen data. This is the problem statement. I'm being asked to evaluate some statements about how the model works and what its output looks like. This statement describes how OMP works. It adds features one by one based on how well they correlate with the remaining unexplained part of the data, residual error. This is true. Using cross-validation, the model will find the number of features that leads to the lowest average MSE across all 5 folds. This ensures a robust model not overfitting on a particular subset of the data. Increasing the number of folds in cross-validation, CV, means running the model training more times, increasing computing time. I'm using orthogonal matching pursuit with cross-validation. OMP-CV is a technique that intelligently picks the most important features from a dataset to build a predictive model. The CV part means it uses cross-validation, which helps avoid overfitting and gives a more reliable performance estimate. OMP-CV works iteratively. Imagine it's like building with Legos. I start with nothing and add one Lego brick, feature, at a time. I select the brick that improves the model the most at each step, based on how well it explains the data I have remaining. OMP stands for Orthogonal Matching Pursuit. It's the core algorithm inside OMP-CV that does the actual feature selection. It does this by repeatedly selecting the feature most correlated with the currently unexplained parts of the data. In other words, it chooses the feature that helps me best explain what's left. I have 500 different data points, each described by 100 different characteristics, or features. Think of each point as a customer and each feature as an aspect like age, income, or buying habits. After the iterative process, I'll have a smaller set of the most important features. This subset will give me almost the same accuracy, but with fewer features, making the model simpler, faster, and easier to understand. Think of it as only using the essential Lego bricks to build my structure. After selecting the features, I'll build a regression model that only uses these selected features. This means I build my model solely on the most useful Lego pieces, not all 100, improving efficiency and reducing complexity. My final model will show me how much each of the selected features contributes to the prediction. These contributions are represented by coefficients, and I only get coefficients for the features I chose. The unselected ones implicitly have a 0 coefficient. They are not part of my optimized model. To ensure the accuracy and reliability of my model, I use 5-fold cross-validation. This means I split my data into 5 equal parts and train my model 5 times, using a different part for testing each time. This process helps avoid overfitting the model to a specific subset of data and gives me a better sense of overall performance. I'm working with a dataset containing 100 different characteristics and 500 individual observations. Think of it like 100 different pieces of information collected on each of 500 people. This is the data I'll use to build my model. Let's do it. To prevent overfitting and improve reliability, I'm using 5-fold cross-validation. I'll split my data into 5 separate groups. I'll then train my model on 4 of the groups and test it on the remaining group. I'll repeat this process 5 times, using a different group each time for testing. This gives a better estimate of how well the model will generalize to new data. I'm using the orthogonal matching pursuit, OMP, algorithm, specifically a version with cross-validation. OMP is a clever algorithm that helps me select the most important features from my dataset to make accurate predictions. The orthogonal part means it's clever in how it selects the features to avoid redundancy. The matching pursuit part means it iteratively refines its selection. Adding cross-validation means that this method selects the best number of features, not just blindly picking some of them. OMP works iteratively, selecting features one by one. At each step, I'll select the feature that is most correlated with the remaining error from previous steps. It's like building with Legos. Each step adds a brick that reduces the error left over from the previous building step. The iterative feature selection is actually quite intuitive. I'll start with all features and, step by step, I'll identify which individual feature is most helpful in explaining the remaining differences I see in my data, and add that feature to my model. I keep repeating the process until I don't see any significant improvements. After the iterative selection is complete, I'll use the results from my 5-fold cross-validation to determine the optimal number of features. This number will help me minimize my prediction error. The final model will only use coefficients for the features that were selected as optimal. I'll evaluate my model's performance using mean squared error, MSE. This tells me, on average, how far off my predictions are from the actual values. Lower MSE is better, meaning more accurate predictions. I'll explain OMP, which stands for orthogonal matching pursuit. It's a greedy algorithm. Think of it like this. You have a bunch of puzzle pieces, features, and you want to build a picture, predict your outcome. OMP cleverly picks the piece that best fits the current incomplete picture at each step, leaving out less helpful features. It repeats this until it's satisfied with the picture's accuracy. Pretty smart, right? This combines OMP's feature selection power with cross-validation to make sure that what works well in one part of the dataset also generalizes well to other parts. The model avoids being too lucky or coincidental. I think of it as a double check. We're dividing our dataset into 5 groups and training the model on 4 of them, and then testing on the remaining 1. We do this 5 times so each group gets a turn as the test set. The outcome helps us avoid overfitting our model. After running OMP, I won't be showing you coefficients for all 100 features. That would be inefficient. I'll only be reporting those coefficients for features that were selected by the model. The others are implicitly 0. It's like saying you only need a few of the puzzle pieces to create a meaningful image, and not mentioning the rest. The model uses mean squared error, MSE, to evaluate performance and decides how many features to include for optimal prediction accuracy while minimizing this error. It's like finding that sweet spot of features for the best prediction, without sacrificing accuracy. Finding the perfect balance is key. We can always achieve that. We have 500 data points, each described by 100 different characteristics or features. This is our starting point. I use orthogonal matching pursuit, OMP, a powerful algorithm for feature selection. OMP iteratively selects features, one at a time, that best explain the data. The cross-validation part means I evaluate the model's performance using different subsets of the data to find the best number of features to use, preventing overfitting. I'm working with a dataset that has 100 different characteristics, features, and 500 individual data points, samples. To find the optimal number of features, I'll split my dataset into 5 equal parts. I'll train the model on 4 parts and test it on the remaining part. I'll repeat this 5 times, each time using a different part for testing. This gives me a robust and reliable performance estimate. I select features step by step. In each step, I choose the feature that is most strongly correlated with the part of the data my model hasn't yet explained. I continue this process until a stopping criterion is met. It's like solving a puzzle, one piece at a time. I'm using orthogonal matching pursuit, OMP, as a regression model. This means I'm trying to predict a continuous value, like a house price, based on a subset of the features. After the model is trained, I'll only have coefficients for the selected features. These coefficients show how strongly each selected feature influences the prediction. Features not selected implicitly have a coefficient of 0. I evaluate my model using mean squared error, MSE. The MSE measures the average squared difference between the values my model predicts and the actual values. A lower MSE indicates a better model. After cross-validation, I determine the number of features that gives me the lowest MSE. This is the optimal number of features to use for the best predictive performance. I'm using orthogonal matching pursuit, OMP, a powerful algorithm for feature selection. The CV in orthogonal matching pursuit-CV stands for cross-validation, meaning I'll use multiple rounds of training and testing to find the best model. I have a dataset with 100 different features, like height, weight, age, etc., and 500 different samples, like individual people. This is what I'm using to train my model. To avoid overfitting and get a better estimate of the model's performance, I'll split the dataset into 5 parts. I'll train the model on 4 parts and test on the remaining part. I'll repeat this process 5 times, using each part as the testing set once. This way I get a really good idea of how the model will generalize. OMP works iteratively. It starts by selecting the feature most correlated with the target variable. It then updates what's left, selects the next most correlated feature, and repeats this process until it's found the best set of features. In each fold of the cross-validation, I'll train the OMP model and then evaluate its performance using a metric like mean squared error, MSE, which measures the average squared difference between predicted and actual values. Lower MSE is better. After cross-validation, I'll choose the number of features that resulted in the lowest average MSE across all the folds. This is the sweet spot, where the model is both accurate and avoids overfitting. My final model will only output coefficients for the features selected during the iterative process. I don't store coefficients for features that weren't chosen. Those implicitly have a coefficient of 0. The model automatically picks the number of features that gives the lowest average mean squared error across the 5 folds of cross-validation. This is how I ensure it's generalizing well. The algorithm picks features one by one. Each time, it picks the feature that correlates most strongly with whatever error is left over from the previous features. This way, I'm systematically reducing the error. This is incorrect. The _coa__ attribute only shows the coefficients for the asterisk selected features. Unselected features are implicitly assigned 0 coefficients. They are not explicitly stored. Increasing the number of folds, CV, means more rounds of training and testing, and thus, significantly, more computation. I'm using orthogonal matching pursuit, OMP, a powerful algorithm that selects the most important features one by one. The CV part means I'm using cross-validation to find the best number of features to use, which helps prevent overfitting and makes the model more reliable. This is like trying out different numbers of ingredients in a recipe and choosing the number that tastes best on average across different batches. OMP iteratively selects features based on how well they explain the remaining variance in the data. I have a dataset with 100 different characteristics, features, for each of the 500 samples. Imagine it as a spreadsheet with 500 rows and 100 columns, each column representing a different feature. The algorithm uses these features to predict or understand something about the samples. To evaluate the model's performance fairly, I'm splitting the dataset into 5 equal parts, folds. The algorithm trains on 4 parts and tests on 1, repeating this process 5 times, each time with a different part as the test set. The performance is then averaged to give a reliable estimate of how well the model generalizes to unseen data. This is like trying 5 different test versions of the recipe to see which consistently works best. The core of the process is iterative feature selection. The algorithm starts with no features selected. At each step, it selects the feature that best explains the remaining error from the previous step. It's like solving a puzzle piece by piece. You identify the most obvious piece first, then add the next most obvious one, until the picture is complete. Very cool, huh? After the process, I only get coefficients, numbers showing the importance, for the features that the algorithm decided were important. I don't get coefficients for the unimportant features because they weren't selected. Think of it like only reporting the grades for the exams you actually took. By using cross-validation, I find the best number of features to include in the model. I do this by testing different numbers of features and choosing the one that minimizes the mean squared error, a common measure of how well the model predicts the data. This is like finding the perfect number of ingredients for our recipe, not too many, not too few, to get the best average taste. Once the optimal number of features is determined, I build the final model using only those features. This provides a more efficient and potentially more accurate model than using all 100 features. This is our final, delicious recipe. I'm ready to bake this.